Hello everybody. Today we actually explain the operation of bipolar transistor and the MOS transistors in the real application. Last video, please review that it's explained the structure, how to make transistors and the characteristic. Two key important things: transistor, bipolar transistor go by exponential curve, and the MOS transistor goes to square curve, the voltage square. And bipolar transistor is rather current driven transistors, and MOS is a voltage driven transistor. Okay, the first circuit you learn is actually in the bipolar transistor something like this, and this is R2 and this is R1, and the output goes there. Now what is the input? First one is amplifier. It's audio amplifier. There is a frequency audio signal coming in. Okay, now we cannot directly apply it. What we do is we through this proper capacitor to extract only AC signal, and we have to set the operating point of transistor by input impedance transistor. This is RL and R. Say R3 and R4, okay, and R3 R4 is a voltage divider, and set this voltage. And what we do is we set this voltage, and for this audio frequency, certain frequency range, this capacitor is almost zero impedance, so the base get this AC signal. And now you remember, if transistor's characteristic, it goes exponent and saturate. Okay, and since the base voltage change, however, there is a ICE current flowing on the on state, so we have a kind of fixed VVE. It's about 600 millivolt. So this one is called emitter follower, means emitter voltage follow the base, because say this signal is like a couple millivolt. Okay, so 600 millivolt doesn't change, because IEE will not change that much. What it changes is this voltage change. So there is a, say, fixed voltage base. The 600 millivolt below this, if this is 2 volt, 1.4 volt, right? And this is a DC voltage, okay? And current 1.4 divided by R1 is going to determine RCE, and RCE, suppose this RCE, ICE, this is the operating point. Okay, now this AC writing here is going to be 1.4 plus E volt R1. How about this voltage? This voltage is going to be ICE. This is ICE. The R2 times ICE. Okay, so voltage output is going to be the 1.4 plus E R1 R2 this is the voltage, right? So output voltage V out is going to be the ratio of this, and this determine the DC point 1.4 times. Say this is much smaller, say 1 volt, so it's going to be 0.4 volt, and 0.4 volt R2 R1 is going to determine the voltage here. This is DC voltage, but the AC voltage is going to be, it's amplified. So what happened is, say this is VBE and AC is writing here, okay? And output is going to be ICE is going to change and multiply by this ratio is going to be V out, okay? And you put the capacitor here to extract only component, the AC component. So this is going to be E out, and this ratio is going to determine the amplification in this configuration. So this is much predictable circuit because it's controlled by R1 R2 ratio, the amplification. Okay, so this amplification, the pretty much linear if input signal is small and amplify the signal. However, this is like a low pass. Here's a low pass, and there is the capacitor on the transistor. This acts like a high pass. The collector node has a capacitor, so frequency response is like a low pass. Certain point, this transistor start amplifying and become the high pass effect come out, the limited range of amplification and frequency F2. Okay. Now, in order to improve this, we can put this capacitor here, and what this capacitor does is, when AC frequency is high, this effective impedance here becomes small, right? So because of this capacitor, so what happened is this ratio actually R1 is going to be parallel with C, and depending on frequency R dash 1 become much smaller, so it's gonna help amplifying at the higher frequency and finally drop. So this amplification frequency range increase. Okay, this kind of capacitor, when I learned this first time, I was puzzled by this. Why you put the capacitor here? And it took a long time to understand why. It's increase the range of amplification and amplification factor at the higher frequency. So it doesn't go down, it's extend. High fidelity audio system, you need a linearity across the frequency range, and yeah, otherwise the sounds skew, it sounds different. Okay, so this kind of improvement capacitors there, and output goes out from this capacitor, go to the next stage. So it's go usually preamp and actual amp operating at much higher current, and output amp. So go through several stages. So if it's 10 times, 10 times, 10 times, it's going to be 1000 times initial 2 millivolt. If it's come from the some kind of media, it could be or IC chip. The audio signal can be small, but we can amplify to 2 volt, and that goes to speaker. Okay, so that's the bipolar. MOS amplifier is basically same. R1, R2, and use a P channel in this case, and this is E in, audio signal come in. You have to set the operating point of transistor by this R4 and R3. Usually you use a high resistor here, so this signal is going to translate to the gate voltage very well, and this drain and source, exactly same operation, but in the CMOS P channel there is a threshold, and this is not exponent, this is the square, voltage square, and VT. You have to make sure this operating point is above this point. DC point, operating point is above here. Then input voltage goes, this is I DS. Okay, and that's AC signal is multiplied by R2 over R1. The same theory goes. Okay, you have to be careful that when you set the operating point of this transistor, make sure it's above the threshold. So it's entirely same, but this is the voltage squares. Bipolar was exponent. So if you listen carefully, the audio system made with bipolar and the most, some people with a very good ear can feel a little bit different. Okay, that's because of the non-linearity is different. Some people prefer the vacuum tube, because vacuum tube has entirely different curve. So entire signal is skewed. It's not complete linear. So that's how the amplifier is created. That's analog. Digital, you operate at the saturation. So you swing operation into entirely high or low, and when it's saturate, it's go extreme one side of saturation to other side of saturation. For example, you put P channel and N channel like that. So you you drive. This is logic in voltage. V out. This becomes inverter, because when this is low, it's close to zero. It is shut off, and this one close to V drain is 5 volt or maybe 3 volt. Goes up, and this is gonna be on, and this is off. So V out is going to be, if this goes low, V out goes to high, all the way the highest voltage. And when V out, V in goes high, then opposite happen. This shut off, and this one shut the on. All the charge here, output node charge, is drained out, and this voltage goes low. They used to be called NMOS. So NMOS is like that. This instead of P channel, you use a resistor, and you can do the same thing, except that this, when you turn off this transistor, this voltage goes up, and this is gonna be slow rise. When shut off, relatively quick, but when you shut on, it's going to be very slow. Okay, for this reason, NMOS circuit is no longer used. This is MOS is a P channel on the top. Okay, then it's going to be much better switching characteristic. Also, but NMOS didn't have a problem, but this MOS has a new problem. What kind of problem? When you drive, this kind of MOS output, when you drive TTL circuit, this is the chip boundary. Okay, the problem is when this become off and this become on, that means whatever the capacitor here is going to be charged up, right? But there's nothing to really this accelerate to this rise time, because this is the TTL is strange. It's a high impedance for high. Low is not the high impedance. When this is on, the current is drawn like this, and it's shut off right away. But when this is off and this is on, there's nothing really to charge up. Often, in order to improve rise time, like this, you have to add extra resistor here, like NMOS, this guy. Okay, so this kind of problem happen, and but it's happen only at the boundary of chip between MOS driving the bipolar circuit. Anyway, this is a little bit more details. Bipolar transistor, this is like a NMOS type bipolar logic. When this is off, then this voltage goes up high, and this is kind of slow because of capacitor here. When this is on, then this gonna drive down, and this output voltage goes low. And of course, using active transistor instead of resistor, this was done in the bipolar logic circuit first and imported to here in the MOS. We can do this. The only problem is bipolar, the transistor, when it's saturate, it goes all the way down here, and no more depletion layers. It's all filled up with carrier, and when you shut off, this voltage, it cannot go up high quickly. It goes very slow. The reason is this one, you have to deplete carrier inside the NPN junction, and depleting carrier is very slow process because it goes recombination. Recombination means hole and electron, they pass the electricity together and create the depletion layer. So the first generation of bipolar logic TTL was very slow in the rise time, and they made improvement, Schottky TTL. What Schottky TTL is, they put forward Schottky transistor diode from base to here. And what the Schottky diode does is, Schottky diode is much smaller voltage than VVE. Say VVE is 600 millivolt, Schottky diode is like a 300 millivolt. So when it goes down, it doesn't allow to go to saturation all the way. It stops here. And what's happened is necessary current come from base. So the circuit is going to change a little bit, but it's stopped here. So rise time is going to be much quicker. So usually it's very slow rise time like that. It's become like this. So this much improvement on the speed. Okay, in the switching, how you measure the speed? You measure the speed at the digital threshold to threshold this time. If rise time is slow like that, then this much more delay. Okay. So they created Schottky TTL, Schottky logic, which has basically a Schottky diode cross base to collector. Again, just like this NMOS problem and this MOS problem with external TTL, the digital circuit, I think switching is not that issue. The issue is how to get very effective switching time. This is better than this for sure. And this is better than this. And this time, sometimes ringing is called ringing. This has to be controlled, because excessive ringing is going to cause a noise on the IC chip, and it's affect the neighbor circuit. But this is the issue in the digital circuit. Okay, and this happen again in the LSI chip design, because when you have gate driving AND gates, you can't drive more than certain number. It's called fan out problem, because each gate input has a capacitor, and total capacitor becomes so big, this driver, you have to use higher current drivers, high power driver, to drive many gates. Okay, that's another issue in the logic design. Okay, finally, logic design, actually, if you have NAND gate or NOR gate, this is NOR or NAND, just one of them, either this or this, basically you can design any kind of logic, right? Think about it. If F equals A, B plus, this is a logic equation, A, C bar plus B bar C, this kind of logic, right? This can be converted to NAND again, AB, A, C bar, B bar C, right? This is Morgan's theory. The same way you can convert this to NOR only. So just designing a single gate, either NAND or NOR, basically you can create any kind of logic element in the design. The even latch and the flip-flop, we talk about this next video. Please wait for the next video. Can be created using NAND and NOR only. So logic design is basically everything, either this or this, depend on what you have, or you can combine them together. And actually, if you have a logic equation, then computer can generate logic diagram. Right? This kind of logic diagram. Okay. But there are a lot of issues you have to pay attention to, latch and flip-flop. So we talk about this in the next video. Okay, that's all for today. If you like this video, please subscribe and click like, and wait for the next video.